Dear students, welcome to this session. In the previous session, we looked into what is a three-phase synchronous generator, and we looked into what is the principle of operation, the principle of operation of an alternator, and we looked into the constructional details of an alternator. The three-phase synchronous generator, it is also called as an alternator, or it can be also called as a AC generator. So all those names are exactly the same. What is the principle it works on? It works on the principle of electromagnetic induction. That is, whenever a flux linked with a coil or a conductor changes, an EMF is induced inside the that particular coil or the conductor. So that is the Faraday's first law. It works on that particular principle. And how the alternators are constructed? The alternator construction has two major parts. One is called as a stator, that is the stationary part, and another one is the rotating part, that is called as a rotor. And the stator is it will be in the outer part, and it will be inside the frame. Okay, so this would be the frame. Inside that we will have the stator, and this is made with a silicon steel material, and on the inner periphery it will be having a slots, and inside those slots we will be having the winding. That winding is a armature winding. So here inside those slots we will be having a three-phase winding, and it will be connected in a star, and the common node is connected to the ground, and these are the three wires of that particular three-phase winding. So normally we label it as R phase, Y phase, and the B phase. So the stator will be accommodating the armature winding, which is a three-phase and star connected, and this is the air gap between the stator and the rotor. And this rotor, there are two types of rotors. One is a salient pole type rotor, and another one is a non-salient pole type. And salient pole type is also called as a projecting pole types. So you can see the poles are projecting out, and non-salient type is a cylindrical structure. It will be having a cylindrical structure, and this rotor will be mounted on the shaft. Okay, and for the salient type, we will have this protruding poles. You can see the projecting poles, which are mounted on, this is a cylindrical steel, which is made of a steel. It is a cylindrical frame, and on top of that these poles are mounted, and this cylindrical frame is mounted on the shaft. And on the rotor we will have a winding. It is just a simple one winding. All this winding is a series, and this winding is connected in such a way that this particular winding on this pole shoe will be such that if it creates a let's say north pole, then the other one, the direction of the winding would be in the opposite direction, so it will be creating a south. So we will have a alternating north south north south. That is how we do the winding, and those both the ends of those two windings are connected to two slip rings. Okay, those two slip rings are connected to the external DC supply. We give the DC supply, direct current to the rotor field winding, so that, and how we give that current? So this is the DC supply that is connected to the brush, and the brush will be connected on top of just the brushes will be touching the slip rings. So whenever this rotor rotates, the rings will also rotate, and the brush will make a firm contact with those rings, and those two rings are connected as a positive negative, and that is the whole winding here. So when DC supply is given, current will start flowing in that particular field winding. So this winding is called as a field winding, which is done on the rotor, and the three-phase winding that is done on the stator is called as a armature winding. So this is a salient type. In the non-salient type, similar winding would be there, but the structure of the cylinder would be structure of the rotor would be cylindrical. Okay, so that is the construction we looked into the previous session. In this session we will look into what is the working. Okay, now we understood what is the construction, how the alternator works. Now we will take this example. Here we give the DC supply. Once we give the DC supply, let us say this is plus and this is minus. DC supply will have a polarity and current will flow in only one direction. Let us say the current will start from this positive end and it will go to this, through this brush it will go to this slip ring. Okay, and through that slip ring it will start flowing into these windings. So this is the path. So all this is connected in series. Okay, and the other end will come back and connect to the other slip ring. Okay, and another slip ring is connected to another brush, so that forms a negative. Okay, so I will repeat again. The field winding is what, which is connected on the rotor. It is connected to DC supply. Let us say DC supply is, this is plus and this is minus polarity. The current will start flowing from the positive polarity and it goes to through the brush, through the ring. It will go through this winding. This is the one end, so it will flow through this particular winding, and all these windings are connected in series. It is the same wire or the same coil, and it will come, the other end is connected to other slip ring, and through the other brush it is connected back to the negative. So that is how a steady current will flow in the field winding. When the field winding is excited, that is, it is given with a DC supply, a current will flow in all these windings, and we know what happens when a current flows through the coil, a magnetic field is created. So all these poles will be having the magnetic field. So the winding, I explained, the winding would be in such a way that if it is a north pole, then the next would be south, north and south. That is how we will have the we will have the alternating poles, north south, and the poles will be always in pairs. Okay, we will not have like a 3 poles. We will always have even number of poles, so always the poles will be in pairs. Now what has happened, the current DC supply is given, current is flowing through the magnetic field winding, and magnetic field is created. Now this rotor is rotated by an external mechanical energy. So using the mechanical energy we rotate this rotor. When this rotor starts rotating, what happens, the magnetic field will also start rotating, and you can see all these armature winding conductors, they are static. So they are static, but what is happening, the magnetic field is moving. So here comes the Faraday's first law. That is the principle of operation of a alternator. Whenever a flux linked with a coil or conductor changes, an EMF is produced. Let us assume there is one conductor here. When this rotor starts moving, the magnetic field also starts moving. Let us say the conductor is here and this is north and south. So north will start approaching towards the conductor. Okay, and once it passes through that conductor, the south will come. So the conductor will go through a north south. It will be exposed to those poles and that magnetic field. That is how the EMF. So this particular conductor or the coil, it is experiencing a constant change of magnetic field, because we are rotating this. Every conductor on the armature winding are experiencing a change of flux. So when change of flux is happening, the flux linked with the conductor is changing. All these conductors, they will induce an EMF, and these conductors are connected in such a fashion. they will add up. So there is a three-phase winding. If you remember, there are three sets of winding here, or three phases of winding, and conductors of each phase are connected in series, so they will add up the voltage, and that is how they will produce the phase voltage, and that voltage would be available at these three terminals. So what happened, we gave the DC supply, the current started flowing in the rotor field winding, so that will create a magnetic field. This rotor is rotated with a mechanical external mechanical energy. So it depends, we talked about this in the previous session. There can be hydropower plant or thermal power plant, different kind nuclear power plant. So that particular energy is used to rotate the rotor. When rotor is rotating, magnetic field will rotate. The conductors, okay, on the armature winding, they start experiencing the change in the flux. So whenever there is a change in the flux, a magnetic change in the flux, and EMF is induced in those conductors, and that EMF altogether it produces the three phase. There is a three phase winding, so we get a three phase output. So for the given input for the mechanical energy, we get the three phase output. That is how the alternator works. Next we will see the frequency of the induced EMF. So we know that in the previous slide we talked about how the working of the alternator, how three phase voltage is generated. Since there is a the rotor is rotated with a certain speed, and there are n number of poles, the frequency will depend on what is the speed of that rotor and how many poles are there, how many numbers of poles are there. The frequency of a induced EMF in a armature conductors depend upon the speed and the number of poles. What is an armature conductor? Armature conductor, it is a part of the armature field armature winding, which is on the stator. So they are just talking about one conductor. So what the frequency depends on, how fast we are rotating that rotor and how many poles are there. Okay, so based on that we will have the frequency. Before we get into the next step, we will understand, if you remember, generation of a AC voltage. Okay, so in generation of the AC voltage, you have seen a conductor has been rotated in the magnetic field. When it sweeps through a pair of pole, means north and south, one cycle of voltage is created. Correct? Consider a stator conductor that is successively swept by north and south poles of the rotor. If a positive voltage is produced when north pole sweeps across the conductor, similar negative voltage is induced when south pole sweeps by. This means that one complete cycle of EMF is generated in the conductor as a pair of poles passes, that is one north pole and adjacent south pole, following south pole. The same is true for every other armature conductor. To understand this, just I will go back, I will show you the slide. So this is the slide. If you remember, this is the slide we looked into when we are talking about the generation of a single phase voltage. So here we have north pole and south pole. We assumed one conductor that is rotated in this particular magnetic field. So position number 1, 2, position number 1, 2, 3, 4. So it is rotated like this. When this conductor is rotated like this, the direction of motion and the direction of the magnetic flux are the same. Okay, so angle between them is 0. The flux cut by the conductor is 0. Voltage induced is 0. So if we plot it on the graph, so this is the 0 voltage. When conductor moves to position number 2, the direction of motion is like this and the direction of flux is like this. Angle between them is 90 degree. So the flux cut by the conductor is maximum, therefore EMF induced at this position is maximum. So at position number 2 maximum EMF is produced. Again the conductor will move to this position, where again the direction of the motion and the flux are same, angle between them is 0, so flux cut is 0, that is the position number 3. And when it comes back to the position number 4, the angle, the direction of motion and the direction of the flux, it is 90 degree, so the flux cut by the conductor is maximum, so EMF induced is also maximum, but now it is under the opposite pole, so the EMF induced would be in the opposite direction. So this is position number 4. This is the 4, you can see the maximum value of the EMF. And when it comes back to the original position, again the EMF induced here is 0. Now you can see this conductor went through a pair of pole, north, south and back. So whenever it is going through a pair of poles, it will generate one cycle of EMF. I hope that is very clear. Now here the difference here is we took the magnetic field. If you see the magnetic field, it is static and conductor is rotating. In our example, the magnetic field is rotating and conductors are static. So I will just show you the first diagram where you will understand. Now you can assume the conductor is sitting here. Now this magnetic field is rotating. Let us say this is north, this is south. Now if this is the conductor, now it is under north, and when it moves, this pole will come here, that will come as south. So this conductor will experience north south. So that is the way. So whenever one conductor it passes through a pair of poles, means north south, one cycle of EMF is induced. Means if there are two poles in one revolution, there are one cycle is created. If there are four poles, okay, if there are four poles in one revolution or in one rotation, two cycles will be created. Suppose there are 8 poles. If there are 8 poles, means what? The conductor will go through north south, north south, north south, north south. That is the 4 times it is going through a north south pair, means it will generate 4 cycles. So whenever there is a one rotation, it will generate 4. When we have 8 poles, it will generate 4 cycles. When we had 4 poles, it generated 2 cycles. When we had 2 poles, it generated 1 cycle. What if we have p number of poles? Okay, if we have p number of poles, the number of cycles generated would be p divided by 2. Okay, that is what we are going to see the next. So number of cycles per revolution. In one revolution, how many cycles are created? It is equal to number of pairs of poles, that is p divided by 2. Means if there are 8 poles in one revolution, the conductor will go through north south 4 times. So that is why we have p divided by 2. So how many cycles per revolutions of EMF induced? P divided by 2. And for number of revolutions per second, how many revolutions we will have per second? N is what? Rotor speed in RPM, rotations per minute. So how many rotations are happening? Rotations or revolutions are happening per minute? N number of rotations. So if let us say alternator is rotating with 1000 RPM, that means what? 1000 rotations per minute. Means in 1 minute rotor is making 1000 rotations, or 1000 rotations are made in 60 seconds. That is, the number of revolutions per second is n divided by 60. Now number of cycles per second. So if we multiply this and this, number of cycles per revolution into number of revolutions per second. So what will happen? Number of revolutions in the denominator here, and here it is numerator, it will get cancelled. What is left is number of cycles per second, and we know what is number of cycles per second, that is the frequency. Therefore number of cycles per second, how many cycles are there per second? It is multiplication of this factor and this factor, that is p divided by 2 into n divided by 60. So we get it as n into p divided by 120. Okay, but number of cycles of EMF per second is the frequency. We know what is the frequency. Frequency is number of cycles per second, number of cycles per second, which is nothing but f. Therefore we get the formula f is equal to n into p divided by 120. Now what is n? N is the rotor speed, and what is the p? P is the number of rotor poles. So how the frequency gets calculated? It depends on how fast the rotor is rotated and how many poles are there. And all of you know the frequency of supply is constant in every country. For example, in India 50 Hz is the standard, and it has to be kept 50 Hz. Some other countries will follow some other frequencies. For example, United States of America, it follows a frequency of 60 Hz. For India, we have a frequency of 50 Hz. Now in order to have 50 Hz of supply, we know that for a given alternator, so for a given alternator, number of poles are constant. You cannot change the poles, number of poles are constant. So how that 50 Hz is maintained for the given alternator? It is maintained using the speed of the rotor. So the speed, the rotor is rotated in such a speed that is called as a synchronous speed, so that the required frequency is generated. Okay, and we represent this as a synchronous speed with ns. Okay, we will see that in a later session. So this is an important equation. Frequency of a induced EMF, f is equal to n into p divided by 120. So this will be useful in our problem solving. Next, we know now what is the frequency of the generated EMF. Now we have to find what is the equation of that particular generated EMF. So EMF equation of an alternator. Let us assume Z, number of conductors or coil sides in series per phase. So how many conductors are there? Z is the number of conductors per phase. So if you remember, if you see this equation, EMF equation, we are going to derive it for the phase, only one phase. And alternator, it is a 3-phase alternator. It generates 3 phases of the voltage will be there. We are going to derive the equation for one phase. Okay, so most of the parameter you will see is per phase, so you have to be very careful. Z is number of conductors per phase, and what is 5? Flux per pole. So flux per one pole in Webers. P, what is the P? Number of rotor poles. And what is N? N is the rotor speed. So this is the speed with which we are rotating the rotor, and it is represented in rotations per minute or RPM. In one revolution means we are going to consider one revolution. Let us say, I will show you the diagram again. This is the, let's say this is the conductor. One revolution means what? Let us assume this is the starting point, and it will rotate, okay, all the way, and this will come back to this position. That is a one revolution. Okay, we will consider in one revolution each stator conductor is cut by P into 5 Webers. Okay, so I will go back to the diagram again. Let us say I have a conductor here, and if this conductor, this is a static, if this rotor makes one revolution, okay, one revolution, and let us say this has 10 number of poles, this particular conductor will be cut by all the poles, right? So this pole, this conductor experiences the flux linkage from all these 10 poles, and let us say for 1 Weber is the flux per pole. So how much flux it will cut? Number of poles into the flux per pole, that is 10 into 1 Weber, that is 10 Weber, that much flux it will cut. Let us say if there are p number of poles, how much flux it will cut? P is the number of poles and phi is the flux per pole. In one revolution, this conductor will cut P number of poles into flux per pole phi, that is P into phi. We'll go to the equation again. In one revolution, each stator conductor is cut by P into 5 Webers. P into 5 Webers. And how much time it will take to make one rotation? We know if the speed is n is the speed, rotations per minute. How much time it will take for one revolution? It will take 60 by n second. Correct? Now, what is the total flux in one revolution? What is the total flux cut by one conductor? That is d phi is equal to P into phi. And how much time it takes for one revolution? 60 divided by n. So we calculated in one revolution how much flux it will cut and in what time it will cut. Why we are coming here is to find the equation for the EMF. We have to check the Faraday's second law. What does the Faraday's second law says? How much EMF is generated. So it gives the details about how much EMF is generated. And what is Faraday's second law? The magnitude of the EMF generated is directly proportional to rate of change of flux linkage, or we can say in terms of a mathematical equation, that is E is equal to n into d phi by dt. And what is n? N is the number of turns. We are taking only one conductor, so E is equal to d phi by dt. So you can see the next equation. Average EMF induced in one stator conductor is equal to d phi by dt, and we know d phi is p phi and dt is 60 by n. So the average EMF induced in one stator conductor is given by p phi n divided by 60 volts. Now how many conductors are there on the alternator per phase? Z, total Z number of conductors are there per phase. So how much average EMF will be induced per phase? Average EMF per phase is equal to this is by one conductor into Z, that is why p phi n divided by 60 into Z, that is the average EMF induced per phase. Now in the previous slides we found the equation for the frequency. What is the equation for the frequency? F is equal to n into p divided by 120. Okay, or we can say n is equal to 120 f divided by p. Now we will replace the previous equation. I will show you the previous equation. In the previous equation we had this speed, right? This speed of the rotor we will replace with the equation from the frequency, that is n is equal to 120 f divided by p. So average EMF per phase would be p phi z divided by 60 into 120 f divided by p. So if we solve this, we get it as average EMF per phase is equal to 2 into f into phi into z volts, that is 2f 5z volts. And if you remember the AC fundamentals that we did, we know what is the RMS value and what is the average value, and we also know what is the form factor. What is the form factor of a alternating voltage? The form factor is given by the ratio of RMS value to the average value. Now we know that most of the time we represent the alternating quantities with the RMS value. So to get the RMS equation for the RMS value of the EMF equation, that can be calculated as RMS value of EMF per phase is equal to average value per phase into form factor. And for sinusoidal, you can go back and check, for the sinusoidal waveform the form factor is 1.11. Therefore RMS value of EMF per phase is equal to average value is what, 2f phi z into 1.11. Therefore RMS value of EMF per phase, that is represented as capital E with a suffix RMS per phase. So ERMS per phase is equal to 2.22 f phi z volts. Very, very important equation. So what is the equation of the alternator? How much EMF is produced per phase? The RMS value of the EMF produced is equal to 2.22 f frequency. So this is the frequency, and phi is the flux per pole, and Z is number of conductors per phase. Now you can see F is constant, isn't it? F is a frequency is constant, and if I want to increase the voltage, you can increase the flux per pole. If you increase flux per pole, then RMS value per phase will increase. Or what you can do is you can increase the Z. So if you increase the number of conductors per phase, if you increase, the EMF induced, RMS value of the EMF induced will also increase. Okay, so this is the equation. Next, there are two terms, winding factor, we will see it in the next slide, Kp and Kd. Okay, so Kp is called as a pitch factor and Kd is called as a distribution factor. So these two are the winding factors of the armature winding. So how the winding is done on the armature has a influence on the how much EMF is produced. So just here we will take this value Kp and Kd, and in incorporating those two factors, the equation would be ERMS per phase is equal to 2.22 Kp Kd f phi z volts. So we will multiply this Kp and Kd to this equation. So this is the most generic equation for the RMS value of EMF equation of an alternator. ERMS per phase is equal to 2.22 Kp Kd f phi z volts. You must remember this, for this will be helpful in solving the problems. Now sometimes what happens is the number of conductors, instead of the number of conductors, they will give the turns. What is a turn? When we have one turn of winding, one turn is what? It will go in one slide and back of the armature winding, and it comes through another slot. Okay, so there will be two conductors in one turn. Okay, so sometimes the turns T per phase rather than conductors per phase are specified. Most of the time one turn will have two conductors. There can be more conductors per turn, it depends on how the winding is done. Normally every turn, okay, every turn will have two conductors. So that is how we can say Tp is equal to Zp divided by 2. So this is the number of turns is equal to number of conductors divided by 2, or number of conductors is equal to 2 times the turns. So if you represent the equation, EMF equation, in terms of number of conductors, you will use ERMS per phase is equal to 2.22 Kp Kd f phi into Z volts. And if you are representing the equation in terms of turns, number of turns, ERMS per phase is equal to 4.44 Kp Kd f phi into T. So if it will become 2 times if you use T. That is the only thing. If you want, you can just remember this equation, and you remember Zp is equal to 2T, and accordingly you can change the equation. Now winding factors, there are two winding factors. And for your understanding, there is no derivation for the winding factors, just you have to understand what are these two factors. The distribution factor represented as Kd, and it is also called as a breadth factor. What is Kd? Kd is EMF with a distributed winding divided by EMF with a concentrated winding. So the winding we can have as a distributed among all the slots, or we can have the winding concentrated in a few slots. So we can have two such windings. So how Kd is calculated? Kd is the ratio of EMF induced if we had the distributed winding over EMF induced if we had the concentrated winding, and the formula is Kd is equal to sine of, in the bracket, n alpha divided by 2 divided by n into sine of alpha divided by 2. And what is alpha? Alpha is called as a slot angle. And what is slot angle? It is given as 180-degree electrical divided by number of slots per pole. So how many slots are there per pole? So this ratio of 180-degree divided by number of slots per pole will give the slot angle, and n is equal to number of slots per pole per phase. So number of slots per pole per phase. For you just need to remember this ratio, and you should be able to write down the formula. There will not be any problems based on the winding factors. Next one is the pitch factor, Kp. Okay, both this Kp and Kd, you used it in your EMF equation, and for the examination most of the time they will give the Kp and Kd values, or they will ask you to assume. Okay, you can assume Kp and Kd as 1, okay, if it is not given. And next one is the pitch factor, Kp, and it is also called as a chord factor. And what is Kp? Kp is a ratio of EMF induced in short pitch coil to the EMF induced in the full pitch coil. So we can have the coil, the winding done in such a way that we can have the full pitch, or we can have the short pitch. So EMF induced, ratio of EMF induced in short pitch to EMF induced in the full pitch is called as a pitch factor, and Kp is equal to cos beta by 2, and beta is the short pitch angle. Beta is equal to 180 degree minus coil pitch.